Most people think they understand electricity. You flip a switch, current flows through wires, and a light bulb turns on. Electrons move from the power plant through copper conductors into your home, carrying energy that makes things work. This picture is taught in schools. It appears in textbooks. Engineers use it to design circuits. But there's a problem. This picture is fundamentally wrong. Not just incomplete or simplified. Wrong in a way that conceals what's actually happening when you turn on a light. The energy that powers your bulb doesn't travel through the wire at all. It travels through the space around the wire. The electrons barely move. They drift slowly, perhaps a few millimeters per second, while the light turns on instantly. So what's really going on? Where is the energy? How does it get from the power source to the load? The answer reveals something profound about how electromagnetic fields work, about how energy propagates through space, and about a deep misconception that hides in plain sight every time you use electricity. Let's start with what actually happens inside a wire when current flows. A copper wire contains an enormous number of free electrons, roughly one per atom. These electrons are not bound to any particular nucleus. They can move. When you connect the wire to a battery, an electric field appears inside the conductor. This field pushes on the electrons. They accelerate briefly, then collide with atoms in the lattice. They accelerate again, collide again. The result is a steady drift velocity, typically on the order of millimeters per second. If you have a 1-meter wire carrying 1 ampere of current, with a cross-sectional area of 1 square millimeter, the drift velocity is roughly 1/10 of a millimeter per second. At this speed, it would take nearly 3 hours for an electron to travel 1 meter. Yet when you close a circuit, the light turns on essentially instantaneously. How can this be? The answer is that individual electrons don't need to travel from the source to the load. The wire is already full of electrons. When the field appears, all the electrons start moving at once, like a pipe already filled with water. Push on one end, and water comes out the other end immediately, even though individual water molecules move slowly. But this doesn't solve the energy problem. It explains how charge can appear to move quickly even though individual charges move slowly. But energy is different. Energy must be transported from the power source to the device consuming it. If the electrons are barely moving, they can't be carrying much kinetic energy. So where is the energy? How does it travel? The key insight comes from understanding that electricity is not fundamentally about moving charges. It's about electromagnetic fields. When you connect a battery to a circuit, you establish an electric field along the wire and a magnetic field around it. These fields contain energy. The energy density in an electric field is proportional to the field strength squared. The energy density in a magnetic field is also proportional to the field strength squared. These aren't abstract mathematical quantities. These fields are real physical entities that exist in space, and they carry real physical energy. Now here's what most people miss. There's a quantity in electromagnetism called the Poynting vector, named after John Henry Poynting, who discovered it in 1884. The Poynting vector describes the flow of electromagnetic energy through space. It's defined as the cross product of the electric field and the magnetic field, divided by the permeability of free space. The direction of the Poynting vector tells you which way energy is flowing. The magnitude tells you how much energy flows through a given area per unit time. When you calculate the Poynting vector for a simple circuit, something remarkable appears. The energy flows through the space surrounding the wires, not through the wires themselves. Let me make this concrete. Imagine a battery connected to a resistor through 2 parallel wires. There's a voltage difference between the wires, so there's an electric field pointing from the positive wire to the negative wire. Current flows through the wires, so there's a magnetic field circling each wire. The Poynting vector, which is perpendicular to both the electric and magnetic fields, points along the length of the circuit through the space between and around the wires. Energy flows from the battery through the surrounding space into the resistor, where it's dissipated as heat. The wires serve as guides for the fields. They establish the boundary conditions that shape the electric and magnetic fields in the surrounding region. But the energy itself travels through space, through what we might call the electromagnetic field in the region around the circuit. The electrons in the wire drift slowly, creating the magnetic field and maintaining the field configuration. But they don't carry the energy. The fields carry the energy. This isn't a minor technical detail. It's a completely different picture of what's happening. When you turn on a light switch, you're not sending electrons rushing through wires to the bulb. You're reconfiguring the electromagnetic fields in the space around the circuit, and those field changes propagate outward at nearly the speed of light. The fields establish themselves throughout the circuit in the time it takes light to travel the relevant distances. Once the fields are in place, energy flows continuously through space from the source to the load. The current in the wires is essentially a byproduct, a surface phenomenon that maintains the field configuration. The real action is in the fields. To understand why this matters, we need to look at what happens when electromagnetic fields carry energy. Maxwell's equations tell us that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. These fields can sustain each other and propagate through space as electromagnetic waves. Light is an electromagnetic wave. Radio waves are electromagnetic waves. But even in circuits carrying steady currents, where the fields aren't oscillating rapidly, the energy transport is still fundamentally electromagnetic. The Poynting vector applies universally to all electromagnetic phenomena. It tells us that whenever you have crossed electric and magnetic fields, energy flows in the direction perpendicular to both. In a radio antenna, this is obvious. The antenna creates oscillating fields that radiate outward, carrying energy away as radio waves. But the same principle applies to power lines and circuits. The fields extend into space, and energy flows through that space. The main difference is that in a circuit, the fields are guided by conductors, and the energy flows along a particular path rather than radiating in all directions. Now let's examine what this means for the propagation speed. When you close a switch in a circuit, how quickly does the light turn on? The answer depends on how quickly the electromagnetic fields can establish themselves. This propagation happens at approximately the speed of light in the surrounding medium. If the circuit is in air, fields propagate at essentially the speed of light in vacuum, roughly 300 million meters per second. If the wires are embedded in insulation or surrounded by other materials, the speed is reduced by the permittivity and permeability of those materials, but it's still a substantial fraction of light speed. For a circuit a few meters long, the fields establish themselves in a few nanoseconds. This is effectively instantaneous on human timescales. The electrons themselves, drifting at millimeters per second, are irrelevant to this timescale. What matters is the field propagation. The energy starts flowing through space around the circuit as soon as the fields appear, which happens at nearly light speed. This is why the light turns on immediately even though the electrons are moving slowly. Let's make this even more precise. Consider a simple DC circuit with a battery, a switch, and a resistor. Before you close the switch, there's no current and no magnetic field. There's an electric field inside the battery due to the chemical potential difference, but no field along the wires. When you close the switch, the battery drives charge onto the wire surfaces. This charge creates an electric field that extends into the space around the wires and into the wire material itself. The electric field inside the conductor is small but non-zero. It must be non-zero to maintain the current against resistance. The electric field pushes electrons into motion, creating a current. The current produces a magnetic field circling the wires. These fields appear and spread outward from the switch at approximately the speed of light. The energy stored in the battery's chemical bonds is converted to electromagnetic field energy. This energy flows outward from the battery, through the space around the circuit, guided by the conductor geometry, and into the resistor. At the resistor, the electromagnetic energy is absorbed. The electric field in the resistor drives the electrons through the resistance, and the kinetic energy of the drifting electrons is transferred to the lattice through collisions, producing heat. The electrons themselves barely move, but they mediate the energy transfer from the fields to the thermal energy of the material. Here quotes a way to see this that makes it even clearer. Calculate the energy flow through any cross-section of the circuit. If you imagine a surface cutting through the wire itself, you can calculate how much energy flows through the copper. It's tiny. The drift velocity is low. The kinetic energy of the electrons is negligible. But if you calculate the energy flow through a surface surrounding the wire, using the Poynting vector, you get exactly the right answer. The power dissipated in the resistor equals the power flowing through the surrounding space. The numbers work out precisely. This isn't a mathematical trick or an alternative formulation. It's a description of what's physically happening. The electromagnetic fields in the space around the circuit carry the energy. You can verify this experimentally. Place a detector sensitive to electromagnetic fields near a current-carrying wire. You'll measure fields. Those fields contain energy. As current increases, field strength increases, and the energy density increases. The energy is genuinely located in the space around the conductor. Now we come to a subtlety that often confuses people. If the energy flows through space around the wires, why do we need thick wires to carry high power? Why do engineers worry about wire resistance if the energy doesn't go through the wire? The answer is that the wires establish and maintain the field configuration. A wire with high resistance requires a stronger electric field along its length to maintain a given current. This stronger electric field means the pointing vector has a larger component directed radially inward toward the wire surface. Energy flows from the surrounding space into the wire where it's dissipated as heat due to resistance. The wire doesn't carry the energy along its length. Instead, it absorbs energy from the fields perpendicular to its length. Thick wires have lower resistance, require smaller electric fields for the same current, and therefore absorb less energy from the surrounding fields. The energy flows more efficiently past the wire through space rather than being absorbed into the wire material. This is why we use thick conductors for high power transmission, not because they carry energy through their bulk, but because they guide the fields with minimal absorption. Let's examine a historical case that illustrates this principle beautifully. In the 1880s, there was intense debate about how to transmit electrical power over long distances. Thomas Edison advocated for direct current systems. George Westinghouse and Nikola Tesla promoted alternating current. One of the key arguments concerned power loss in transmission lines. When current flows through a wire with resistance, power is dissipated as heat. The power loss equals the current squared times the resistance. To minimize loss, you can reduce either the current or the resistance. Reducing resistance means using thicker wires, which is expensive. The brilliant solution was to use high voltage and low current, which requires alternating current and transformers. But here's what's interesting from our perspective. The engineers of that era thought about power flowing through the wires themselves. They calculated resistive losses in the conductor material. This gave the right practical answers for designing systems, but it wasn't a complete picture of the physics. The power was actually flowing through the space around the transmission lines. The losses occurred because some of that electromagnetic energy was being absorbed into the conductor material due to resistance. The electric field inside the conductor, though small, did work on the drifting electrons, and that energy was transferred to heat through collisions. The conductors were absorbing energy from the surrounding electromagnetic field as it propagated along the transmission path. This becomes especially clear when you look at high-frequency transmission. At radio frequencies, currents flow only on the surface of conductors, not through the bulk. This is called the skin effect. The reason is that at high frequencies, the magnetic field penetrates only a small distance into the conductor before inducing currents that oppose further penetration. The effective cross-sectional area available for current flow shrinks to a thin layer at the surface. But electromagnetic energy still propagates efficiently along the transmission line because it's traveling through the space around the conductor, not through the conductor bulk. This is why radio frequency engineers often use hollow conductors or even just thin coatings of conductive material. The interior of the conductor is irrelevant. What matters is the surface that guides the electromagnetic fields. The energy propagates through space at a speed determined by the permittivity and permeability of the surrounding medium, typically a substantial fraction of light speed. The conductors merely provide boundary conditions that guide the field pattern. Now let's address what determines the speed of this energy propagation. In a typical circuit with wires in air, you might expect the energy to propagate at the speed of light in vacuum, but measurements show it's usually somewhat slower, perhaps 60 to 90% of light speed. Why? The answer has to do with the field configuration. The electromagnetic fields don't exist only in the air around the wires. They also penetrate slightly into the conductor material and into any insulation surrounding the wires. These materials have different permittivity and permeability than vacuum. The effective propagation speed is an average weighted by where the fields have significant amplitude. If substantial field energy resides in materials with high permittivity, the propagation slows down. This is the same reason light slows down in glass or water. The electromagnetic wave interacts with the material, and the speed of propagation decreases. In a circuit, the exact speed depends on the geometry and materials. For parallel wires in air, it's close to light speed. For coaxial cable with plastic insulation, it might be 60 to 70% of light speed. But it's always much faster than the drift velocity of electrons in the conductor. There's a beautiful consequence of this picture that becomes apparent when you think about energy conservation. Energy must be conserved in any physical process. When a battery powers a light bulb, chemical energy in the battery is converted to light and heat in the bulb. Where is that energy during the transit from battery to bulb? In the naive picture where electrons carry energy through the wire, the answer would be that it's in the kinetic energy of moving electrons. But we've seen that the kinetic energy of drifting electrons is negligible. In the correct picture, the energy resides in the electromagnetic fields in the space surrounding the circuit. At any given moment, there's a certain amount of energy stored in the electric and magnetic fields between the battery and the bulb. Energy continuously flows from the battery into these fields, propagates through space, and is absorbed by the bulb. The fields act as the medium for energy transport. This isn't a metaphor. The fields physically contain the energy. You can calculate how much energy is in a given volume of space by integrating the energy density over that volume. The energy density is the sum of electric field energy density and magnetic field energy density. When you add up all the field energy in the circuit at any instant, then account for the energy flowing in through the battery terminals and out through the bulb terminals, everything balances perfectly. Energy is conserved, but it's conserved in the electromagnetic field, not in the motion of charges. Let me give you one more example that makes this unmistakably clear. Consider a transmission line. Two parallel conductors separated by some distance, carrying current from a power source to a load. The electromagnetic energy flows through the space between the conductors. You can place an imaginary surface between the two wires and calculate the Poynting vector crossing that surface. The total power crossing that surface equals exactly the power delivered to the load. No power crosses through the conductor material itself along the length of the line. It all flows through the space between and around the conductors. If you wanted to block the power transmission, you wouldn't need to cut the wires. You could in principle place a barrier in the space between them that absorbs or reflects electromagnetic fields. The power would be blocked even though the conductors remain physically continuous. Now we arrive at the deeper question. Why does nature work this way? Why should energy reside in fields rather than in moving particles? The answer takes us to the foundations of how we understand forces and interactions. In classical physics before Maxwell, forces were thought to act instantaneously at a distance. The sun's gravity reaches out across space and immediately pulls on Earth. Two charges immediately push or pull on each other. But this picture has a fatal flaw. If forces acted instantaneously, information could propagate faster than light, leading to violations of causality. Maxwell's equations changed everything. They showed that electric and magnetic forces propagate at a finite speed, the speed of light. Forces are not instantaneous. They're mediated by fields that take time to propagate. When you move a charge, the electric field around it doesn't change everywhere at once. The change propagates outward as an electromagnetic wave at light speed. Distant charges don't respond until the field change reaches them. This resolves the causality problem. But it means the fields must be real, physical entities. They can't be just mathematical conveniences for calculating forces. They must actually exist and carry energy, because during the propagation time, the energy has to be somewhere. It's in the fields. This insight extends beyond electromagnetism. In modern physics, all forces are understood as mediated by fields. Gravity is mediated by the gravitational field, or in general relativity, by the curvature of space-time itself. The strong nuclear force is mediated by Gluthon fields. The weak nuclear force is mediated by Dugel and Z boson fields. In quantum field theory, particles themselves are excitations of fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. The universe is fundamentally made of fields. Particles are derivative phenomena, localized disturbances in the fields. From this perspective, it's natural that energy resides in fields. Fields are the basic constituents of reality. When we talk about energy flowing from a battery to a light bulb, we're talking about disturbances in the electromagnetic field propagating through space. The electrons in the wire are just one type of field excitation, and they play a supporting role in maintaining the configuration of the electromagnetic field. But the energy transport is fundamentally a field phenomenon. Let's return to the original misconception. Why do people think electrons carry energy through wires? Partly because it's a simpler picture that gives approximately correct answers for many practical purposes. If you calculate circuit behavior using Kirchhoff's laws, treating wires as perfect conductors and thinking vaguely about current as the flow of something through the wires, you get the right voltages and currents. For an engineer designing a circuit, the detailed field picture often doesn't matter. But it's not just simplification, it's a deeper conceptual error about what electricity fundamentally is. Electricity is not the motion of charge. Electricity is the behavior of electromagnetic fields, and charge motion is one aspect of that behavior. The fields are primary. The charges respond to the fields and contribute to the fields, but the energy and information propagate through the fields themselves. When you flip a light switch, you're not sending electrons to the bulb. You're reconfiguring the electromagnetic field throughout the circuit, and that reconfiguration propagates at nearly light speed, carrying energy through space, from the source to the load dot. Their quotes have a philosophical point here about how we understand physical explanation. Often in physics, we have multiple mathematical formulations that give the same predictions. You can analyze circuits using field theory and the Poynting vector, or you can use circuit theory with Kirchhoff's laws and think about currents and voltages. Both give the same answers for many problems. So which one is true? Which one describes what's really happening? The answer is that the field theory picture is more fundamental. It applies in all cases, including radiation, high-frequency propagation, and situations where circuit theory breaks down. Circuit theory is an approximation valid when wavelengths are much larger than circuit dimensions and when fields are quasi-static. But more than that, the field picture explains aspects of the phenomenon that circuit theory simply doesn't address. It tells us where the energy actually is. It tells us how fast signals propagate and why. It connects circuit behavior to the deeper principles of electromagnetism and relativity. This is what we mean by a fundamental explanation. Not just a mathematical formalism that predicts measurements, but a description of the underlying physical reality that shows why those measurements come out the way they do. The misconception about electricity reveals something about how science progresses. We often begin with intuitive pictures based on everyday experience. Things flow through pipes, so maybe electricity flows through wires. These pictures are useful starting points. They let us organize observations and make predictions. But as our understanding deepens, we discover that nature operates on principles quite different from our everyday intuitions. Fields are not part of ordinary experience. We don't perceive electromagnetic fields directly. We see their effects, forces on charges, light and radio waves, electrical power. Building a mental model of fields as real physical entities carrying energy requires letting go of the simpler mechanical pictures and embracing something more abstract and mathematical. This is difficult but necessary. The reward is a deeper understanding of how nature actually works. When you flip a switch and a light turns on, you're not pushing electrons through wires. You're launching an electromagnetic disturbance that propagates through space at nearly the speed of light, carrying energy in the fields themselves. That's the reality behind the familiar phenomenon. That's what's truly happening. And understanding this distinction between the convenient fiction and the physical truth is what separates superficial knowledge from genuine comprehension of nature.